Good morning. So, we talked first of all about conservation of energy, meaning that internal work equals stored potential energy. This external work on the body is transformed into internal work or strain energy, UI. And these two quantities are equal. We talked about there is no friction, there is no other damping factors, etc. I would like to increase this if it is possible. So, for example, in case of the bars, then this load P works on displacement delta, okay? Now this displacement delta then transforms into the energies of these bars, 1, 2, 3, 4, 5, 6, 7, 8, 9 bars, and energy in each equals N axial force squared times associated length divided by 2 times cross-sectional area and modulus of elasticity that we obtained past time. Analogously, for the beam case, that was a truss, now that is a beam. So if there is a concentrated load, then appropriate displacement is denoted here as delta, Greek delta. Appropriate work is of external forces is 1/2 P times delta, okay? 1/2 P times delta. And that equals the integral of the beam, bending moment, so I will call it mz, squared 2EI dx, okay? Now, what happens when there is a concentrated moment? Concentrated moment then works on appropriate slope or angle, theta. So 1/2 m0 times theta equals then to the same thing, m squared 2EI dx. Okay, so as we say, strain energy is a result of the internal bending moment caused by application of the couple moment m sub 0. Once m has become expressed as a function of x and strain energy evaluated, then theta, the measure of slope, can be determined. So what we are saying actually is that theta equals, if we want theta, then it equals this integral from 0 to L, m squared dx over 2EI divided by the moment that caused it, 1/2 m sub 0. Okay, so that is a different way of finding displacement. So here displacement would be integral from 0 to L, mz squared dx, 2EI, yes, 2EI, divided by 1/2 P. That is how we could evaluate things. Look, please, we already learned how to evaluate displacements or proper angles or slopes. However, that is one more way. So that is one more way of finding delta and theta. And we will be using this strongly. So that is actually then 25.1. Okay, I will discuss the examples, because examples are very important. 25.2, and that is this truss. There is this truss. So here in hinge B, so that is 2 feet, that is appropriately, that is 4 feet, then that is 30 degrees, which gives us immediately this value. And there is a load 5 kips. Now we are using method of cuts, and we obtain this picture. So there is 5 kips, and there is this load that is pressing in this member, and load that is extending in this member. So we call it NAB, because that is between A and B. NAB, that is NBC. Naturally, this works to the right, this works downwards, and it should be a compressive force. Okay, then we find these loads from equilibrium conditions, 2.89 kips, that is 577 kips, and 5 kip was given. So we would like to find displacement of this hinge B in horizontal direction. Okay, as a result, there will be the displacement delta. 1/2 P delta equals sum of the energies accumulated in these bars. So 1/2 5 kip delta B in horizontal direction. That equals, look please, 289 we found in NAB, 285 kips squared, length is 2 feet, divided by 2AE. Now this in NBC, that is minus 577 kips squared, 4 feet, 2AE, yes. And then here we found, here we can also make a cut. Here we make a cut, and this cut gives to this result. Okay? And the result is that once we know this 577, then we don't need to find reaction here, because we can project forces in horizontal direction and find that here there is 5 kips. Okay? No sum of the forces in y direction equals 0, we don't need. Only sum of the forces in x direction equals 0. Equals 346 feet, 2AE. So then we get, look, delta B equals, that summation here of all numerators equals 4732 kip times feet divided by AE, and we substitute also the value of AE, okay? 2910 in power 3 kips over inch squared, and that is 0.2 inch squared, that is A. That is A, that is E. So we get 0.0979. I think it's very powerful method. Look, please, we have a test on Thursday, and pay attention. I'm not assigning homeworks on these topics. Why? You are intelligent, smart people. You have a book in front of you. You can solve some selected problems by yourselves without submitting. Okay? 25.3. Now we're talking about the beam problem, because we talked already about the truss. So I have this cantilever beam, and there is concentrated load at the end. And it says a cantilever beam has a rectangular cross section and is subjected to load P at the end. Determine the displacement of the load. Okay. So 1/2 P over P times delta, that is a work of external forces. Now the moment, there is a bending moment contribution and shear force contribution. So I will write mz contribution, and that is Vy contribution. Now we define this Vy, that is factor of cross section, that is Vy squared dx to Ga. G is modulus, shear modulus. That is elastic modulus. So we found that this factor of cross section for rectangular cross section is 6/5 minus P. Okay, shear equals here minus P. Okay, shear force. Indeed, shear force diagram would be like this. That is Vy, and that is negative value P. Bending moment mz. Equals this. Okay? So we have minus P squared dx to Ga. Here will be minus P times x. That is this one. Squared. So we get 3P squared L, 5Ga, plus P squared L cubed, 6EI. Okay? Now, outer actually here shows that this term is very small in comparison with this small. 3/5 P squared over 5Ga is much smaller than P squared L cubed 6EI. Indeed, let us do the calculations. Will be 3P squared L, G, cross-sectional area is BH. Here, moment of inertia is 1/12 BH cubed. So when we cancel, so for example, by L, here we get L squared. Then we get this value. E is not just smaller than 3G, because G equals E 2 in power 1 minus nu. Okay? So we get at the end that 0.9 is much smaller than L over H. Naturally, length is much bigger than height of the beam's cross section, that is H. So therefore, we can neglect by this term, and we get just this term, just this term. 1/2 P delta equals P squared L cubed 6EI. And we get delta equals P L cubed 3EI. That we knew from the beginning of the course. Voila, that we knew. We knew this result. Any questions? Okay, now we are going to another topic, which is very, very, very important in this part, and that is principle of virtual work. Now, that is a very important topic. The principle of virtual work was developed by John Bernoulli in 1717. And like other energy methods of analysis, it is based on the conservation of energy. Although the principle of virtual work has many applications in mechanics, in this text we will use it to obtain the displacement and the slope, okay, on a deformable body. To do this, we will consider a body to be arbitrary shape. Okay, so for example, here there is this arbitrary shape, not just a truss or not a beam, just any shape. And it is subjected to real loads. Okay, look please, suddenly we are using this virtual work, so we will come up to the meaning of this virtual work. Okay, real works P1, P2, and P3. So there are loads. Okay, P1, P2, and P3. Okay, there are 3 loads. We can show more loads, but of course we show just 3. It is assumed that these loads cause no movement of the supports. Okay, that is understandable. However, in general, they can strain the material beyond the elastic limit. That is also possible. Suppose that it is necessary to determine displacement delta of a point A on the body. Okay, so that is this point A. Point A. And we want to find displacement in this direction. So that means, pay attention, the body is arbitrary, that is not a beam, not a truss, so it could be, and I took an arbitrary body. Yes. Since there is no force acting on the A, okay, delta will not be included. Okay? Look, again, let us read, because I would like to read why, because you will be able to read this material. Book is freely available on the web, as we said. That is why I adopted this book, because I would like you not to have additional expense in addition to other many expenses that you might have. Suppose that it is necessary to determine the displacement delta of a point A on the body. Since there is no force acting on A, then delta will not be included in an external work form in the equation when the conservation energy principle is applied to the body. Because if we had load, then we would have 1, 2 P times delta. But we don't have a load here, so we cannot write this. In order to get around this limitation, we will place an imaginary. Can you imagine we had imaginary numbers? Now suddenly we have imaginary load, and we have virtual work. Virtual work means not a real work, but virtual work. Okay, imaginary or virtual force P prime. So P prime on the body at point A. Okay, so that will be P prime here. Such that P prime acts in the same direction as delta. Furthermore, this load is applied to the body before the real loads are applied, before. For convenience, which will be made clear later, we will choose P prime to have a unit magnitude. Okay, if I'm imagining something, I can also imagine that it has value 1. Why? Because it will be easy to get rid of something that is 1. Okay. That is P prime equals 1. Okay, so this is the load P prime that is here. P prime equals 1. Here. It is to be emphasized that the term virtual is used to describe this load because it is imaginary and does not actually exist as part of the real loading. Pay attention. Einstein said imagination is more important than knowledge. Albert Einstein. So in this way, I personally imagine that in a proper time, in the correct time, we will be getting rid of coronavirus and we will be having regular lectures, not lectures by WebEx or lectures that are recorded and put on Canvas. Okay, the external virtual load, however, does not create an internal virtual load, U, okay, in a representative element. It does not create, because it is a virtual load. And U can be related by the equations of equilibrium. Also, because P prime and U, the body and the element, will each undergo virtual imaginary displacement, because if there is virtual load, then there will be virtual displacement. Also, we will not be 25.5 concerned with their magnitudes. Once the virtual load is applied and then the body is subjected to the real loads, P1, P2, P3, point A will be displaced a real amount delta, which causes the element to be displaced. Okay, this element, some length L, will be displaced by additional value dl. So then, look please, we are getting 1 times delta, that is a load, virtual load. Okay, then we will have, that is real displacements now. Delta summation U times delta dl. These are the elongations that systems are undergoing. So that is U is internal virtual load. For some reason, my other pen that I have probably fell down on my way to this room. Okay, so then we get 1 times delta equals U times dl. These are real displacements. Delta is a real displacement, and dl is a real displacement. So, what is this? P prime is an external virtual unit load acting in direction of delta. U, internal virtual load acting on the element. This load acts, why? Because I applied load there at the point A. So the system undergoes change, virtual change. So U is internal virtual load acting on the element. Delta is external displacement caused by the real load. dl, external displacement of the element in the direction of U caused by real loads. By choosing P prime equals 1, it can be seen that the solution delta is obtained. Delta equals this. That is why I chose 1. Of course, if I would have not chosen 1, then I would divide everything by that P prime. So I'm getting the delta equals U dl. Okay, we will now explain this. How do we get how to use it exactly? Analogously, we are doing in a similar manner. If angular displacement or slope of the tangent or the tangent of the point of the body is to be determined at point A, then we are using virtual moment, M prime, having a unit magnitude. Okay, then a virtual coupled moment having unit magnitude is applied. As a result, this coupled moment causes virtual load U theta in one of the elements. And then we will get U theta dl. So 1 times theta equals summation of U theta dl. So M prime equals 1, external virtual moment coupled. acting in the direction of theta. U theta, internal virtual load acting on the element. Theta, external angular displacement in radians caused by the real loads. dl, internal displacement of the element in the direction of u theta caused by real loads. This method for applying, okay, then I put this moment equals 1 and get theta. Theta equals summation u theta dl. Look, please, this is a subtle point. Naturally, Bernoulli was a genius. He did many other things, for example, in fluid mechanics, in other parts of mechanics. This method for applying the principle of virtual work is often referred to as method of virtual forces. Or since a virtual force is applied, resulting in a determination of external real displacement. This equation of virtual work, in this case, represents a statement of compatibility requirements of the body. Now, what is compatibility? Analogous thing we had, for example, when we had this problem in the project 2. So here we said V from the left equals V from the right, and then V prime equals V prime here, left, right. These were compatibility or continuity conditions. Continuity or compatibility conditions. These two beams should be compatible with each other. That is what it should be. So these were continuity conditions or compatibility conditions. So here that the author, Mr. Hibbeler, uses the word compatibility requirements for the body. Also, it is not important here. Realize that we can also apply this principle of virtual work as a method of virtual displacements. In this case, virtual displacements are imposed on the body, but we are not going to do that. Internal virtual work. The terms on the right-hand side, okay, in equation 1434, that is 1434, and 1435, we will get here, represent the internal virtual work developed by the body. The real internal displacements, dl, in these terms can be produced by several different ways. You may say, okay, how do I get dl? How in the world I will get dl? That is your question, naturally. Okay? Then, okay, for example, these displacements may result from geometric fabrication errors, from the change of the temperature, or more commonly from stress. No restriction has been placed on the magnitude of external loading, so the stress may be large enough to cause yielding or even strain bending of the material. So we continue. If we assume that material behavior is linear and the stress does not exceed the proportionality limit, we can then formulate the expressions for internal virtual work caused by stress using the equations of strain energy developed in the previous section. They are listed on the center column here. So we have n squared dx 2 divided by 2EA. Then due to shear force, y, that is n sub x. F sub s, v squared 2GA dx. Bending moment m squared 2EI. Torsional moment t squared dx 2G and j polar. Recall that each of these expressions assumes that internal loading n, v, m, and t has applied gradually from 0 to full value. Do you remember? That is why we have this 1/2. because of graduality. I will depict this. That is this nx. And that is this proper displacement. Analogously, bending moment is applied like this, etc. So that is why we have 1/2, because that is this energy. That is this area. This area equals 1/2. As a result, the work done by these resultants is shown in these expressions as 1/2 of the product of the internal loading and its displacement. In the case of virtual force method, however, the full virtual internal loading is applied before the real loads cause displacements. Before. And therefore, the work of the virtual loading is simply the product of load times proper displacement. Okay, referring to these internal virtual loadings U by the corresponding lowercase symbols N, V, M, and T. Sorry with V, because V we had reserved for displacement. But here, this is a small lowercase big V, shear force. Then internal virtual work, we do not have 1/2. No 1/2. No, that is this internal. So then, therefore, we get internal equals not n squared, but n times NAE. Instead of having n squared, we have then this virtual expression is working on real values of the inner forces. So that is inner force, that is also inner force. That is inner generalized force bending moment and inner generalized force, which is torsional moment or torque. So therefore, we have to sum up whatever that is an arbitrary body. In arbitrary body, we can have an x, we have moment, we have shear force, and we have a torque as a result. So 1 times delta equals summation of all these terms. Any questions? In the following sections, we will apply the above equation to problems involving the displacements of joints on trusses, the points on beams, and mechanical elements. We will also include a discussion on how to handle the effects of fabrication errors and differential temperature. For example, if the real loads are expressed in kilonewtons and the body's dimensions are in meters, 1 kilonewton virtual force, or 1 kilonewton times meter virtual couple, should be applied to the body. By so doing, the displacement delta will be in meters, and the calculated slope will be in radians. I think that is on one hand, difficult topic, but once you sit with yourself and you read the book very carefully, without any disruption, then it is actually a difficult, simple topic. So I will even write it. Difficult, simple topic. By the way, I said difficult first, but then simple second. It's not simple, difficult topic, but difficult, simple topic. Sounds like oxymoron, but this is an expression that I like. It looks difficult in the beginning, but then when you think about, when you read very carefully each sentence, when we have to read very carefully each sentence, not just like this, you know, not like a detective, then it is simple. Okay, we will consider 25A. We will use virtual forces applied to trusses. Okay, then we have this one term, n, small n times n, AE dx. Okay, then if these values are constant, we are taking out, integral equals L. Then we have 1 times delta equals summation, small n times capital N, LAE. Now, what are things here? That is a very, he may have said, come on, we already defined in previous section. If you don't understand something, go there and read. No, he repeats these symbols here. 1 is external virtual unit load acting on the truss joint in the direction of delta. We still did not say where we want to find. Delta is a joint displacement caused by the real loads on the truss. And internal virtual force in the truss member caused by the external virtual unit load. Because if I'm applying external unit load, it is not just we imagined it. When we imagine this load, there is whole things change in the body. Okay, there are internal loads, like always. When we have real load, we have real internal forces. That is what we do to find diagrams of Vy, Mz, etc. Now, N, internal force in the truss member caused by real loads. L, length of the member. A, cross-sectional area of the member. E, modulus of elasticity of a member. You may have said, come on, I don't need to repeat. E, we know already. No, he writes everything, just to remind us again and again. Okay, so we applied this force 1. Okay, and I want this place, so that is a, okay, let us read the problem first. So that is a truss, okay? So there are external loads P1 and P2. Now that is, we want to find displacement at point A. Okay, and there is no load applied here. If I want to find displacement here, I don't need to use method of virtual displacements, or here. But I want to find here. Okay, then we will apply here unit imaginary force or virtual force. Okay, so then displacement I want here. Okay, what happens when temperature change occurs? Well, it's very simple. Truss member can change their temperature, can change due to change in temperature. If alpha is the coefficient of expansion, okay, of the thermal expansion, that is thermal expansion. For a member, and delta T is a change of the temperature, then length will change by delta L equals alpha delta TL. Hence, we can determine the displacement 1 times delta N, that is inner force. And displacement is alpha delta T del L. 1 is external virtual unit load. Delta is a joint displacement. We mean displacement of the joint, okay? And internal virtual force, alpha coefficient of thermal expansion, delta T change of temperature, L is length. Now fabrication errors. Occasionally errors in fabricating of the members of the truss may occur. If this happens, the displacement delta in particular direction of the truss is determined from like this. 1 times delta equals summation n delta L. What is n delta L? It's difference of lengths of the members. Look, please, you are going to some company and you say, I would like the length of these members to be, say, 1 meter. They deliver you the materials and bars or beams. But then very often one it's a bit longer, another is a bit shorter. There is scatter in preparation. So as a result, therefore, we can calculate this delta L, differences in length of the member from its intended length caused by fabrication error. Now, what is a procedure of analysis? Place the virtual unit load on the truss at the point where the displacement is to be determined. The load should be directed along the line of action of the displacement that we want, desired displacement. With the unit load so placed and all the real loads removed from the truss, calculate the internal force in each truss member. Assume that tensile forces are positive and compressive forces are negative. Look, he is repeating even something that is part of us already a long time ago. Real forces, N. Determine the N forces of each member. These forces are caused only by the real loads acting on the truss. Assume that tensile forces are positive and compressive forces are negative. Virtual work equation. Apply the equation of virtual work to determine the desired displacement. It is important to retain the algebraic sign of each of the corresponding N and N forces. If the resultant sum is positive, the displacement is in the same direction as virtual unit load. If it is negative, then it is opposite of the virtual unit load. When applying 1 times delta equals summation n alpha delta TL, an increase of temperature is positive, whereas a decrease of temperature will be negative. When we are using with fabrication errors, 1 times delta n delta L, when a fabrication error causes an increase for a length, delta L is positive, whereas decrease is negative. When applying this method, attention should be paid to the units of each numerical quantity. Notice, however, that the virtual unit load can be assigned any arbitrary unit, pounds, kips, newtons, since N forces will have the same units. As a result, the units for both the virtual unit load and N forces will cancel from both sides of the equation. I think these are very, pay attention, I could have just not copied this page as self-evident, but nothing is self-evident. Please, in your work also, when you will become a boss, you will have other workers, please explain everything, absolutely everything, so that there is no place for misunderstanding or some misconception. Now we will solve some problems. And when we solve problems, indeed, we will see that this method is simple. Okay. So we have this truss. Okay, 1, 2, 3, 4 members. And there is a real load of 100 kilonewtons. What I want to find, I would like to find displacement in point C. What do? I will apply virtual force in that direction. Okay? Then, I will solve first problem for virtual loads. Okay? Virtual forces N. Since the vertical displacement of joint C is to be determined. Only a vertical 1 kilonewton vertical load is placed at joint C, and forces in each member should be calculated using method of joints. It's very simple. We did it, you did it in statics. Then we are using real force, that is 100 kilonewtons. And then we calculate the forces due to these inner forces, I mean, in every member, due to this load. Okay? Okay, now in the virtual system, we can find these loads. Here, this is 1 kilonewton. This is minus 1,414, which is minus square root of 2 kilonewtons. These are zero members. Okay, because indeed, when I cut here, there is no force here in vertical direction or horizontal direction. These are zeros. AB, the small n equals 0. BC, small n equals 0. AC equals minus 1,414. CD equals 1. N, that is this system, minus 100, 141,4, BC, that is BC. That is minus 100, minus 141,4, this is 200. Now we are doing very simple things, okay? How much is small n times capital N times L? Okay, that is, because this is 0, this guy gives me 0. Because this is 0, this summation is 0. Okay? Then here is minus 1,414 times minus 141,4. We get, and then length equals 282. Because 141 times 141. So that will be 200. And then 200 times 282 will be 565.7. Here is 1, 202 equals 400. Summation equals 965.7. So then 1 kilonewton times displacement in C vertical direction. That is C in vertical direction. Equals summation of small and big N L delta E. 965.7 divided by AE. So then 1 kilonewton times delta CV equals this product. And delta CV equals 0.101207 meters. Simple. Simple as A, B, C. It is simple. But in order to understand the concept, you have to spend time. So that is a bit difficult. Some people don't want to spend time. They say, come on, give me the steak on my plate. That is it. I don't want to think. No, engineering is not like going to a restaurant. We have to think by ourselves. Any questions? No. Then we continue. 2512. Pay attention. There are many problems in the book, and you can solve any number of problems. I do recommend you to spend some time with solving some problems here. Why? Because that is how you are learning material. Then you can check in the solutions manual. I made so that the book also has solutions manual available. Then check your solution with solutions manual. That is what you will be doing when you will be an engineer already. Then naturally there is no professor, there is no teaching assistant, there is only a book in front of you. Of course, there is also a colleague with whom you can discuss if he belongs to your team. That is how we will be working. determining the horizontal displacement of the roller, B, of the truss shown here, that is a truss, that is a real load. And I want displacement of the roller, okay, in this horizontal direction to the left. Okay, so I will use virtual forces method. I want in this direction. If displacement is positive, that means that indeed the displacement is in the direction that I said. Otherwise, it is in opposite direction. Okay, so virtual force, I'm applying this load 1 kilonewton. Okay, then these two are zero members. This one is not zero member because minus 1.155 kilonewtons. It depends on the angles, etc. Now real force, so I can find also here the loads. That is 6 kilonewton. Here is minus 12, 10, 39, minus 12. Okay, so I have all of this. Then virtual work displacement. So that is due to temperature change. We don't have it. That is due to manufacturing errors. We do not have it. By the way, in order to find manufacturing errors, then we have to conduct real measurement and find whether the length is shorter or longer, etc. You get a delivery, say, from another source of the beams, then you have to check. Okay, imagine that they are perfect, and there is temperature did not change. Then we get, look please, first two members here, there is 0. So these two members, it's not important. When I multiply this by this is 0. This by this is 0. So only one term will be here. This times this. Minus 1,155 times minus 12. Length is 4 meters. Okay? AE. So that is 250, 10 in power minus 6 meters squared. E, 200, 10 in power 6 kilonewton over meter squared. So that equals, look please, 0.00125 meters. Okay? Simple as pie. So that is it. Any questions? Now I will also give the procedure of the analysis. 2513. Look, I'm not assigning you homework, but if you want, please contact me by email and I will assign you homework. I just want to give you virtual freedom. Why? What does that mean, virtual freedom? You are free to choose any problem in the book that is in front of you, and you try to solve it. Or contact your team members and say, I'm choosing this problem. Can you please also choose that problem? Then we will correspond with each other and compare our solutions. If I know, I will explain to you. If you know, you will explain to me. Okay? The following procedure provides methods that may be used to determine the displacement and slope at a point of any on elastic curve of a beam. Okay, we talked about the trusses. Now we will talk about the beam. Virtual moment small m and m theta. M is just when we apply the load. This is when we apply moment. Place a virtual unit load on the beam at a point and direct it along the line of action of the desired displacement. If the slope is to be determined, place a virtual unit couple moment at this point. Couple is enough, or moment is enough, but he's using couple moment. That is fine. Maybe he's using this couple moment so that we, as reader, will not get astray. Establish appropriate x coordinates that are valid within regions of the beam, where there is no discontinuity of both real and virtual load. With the virtual load in place and all real loads removed from the beam, calculate the internal moment m and m theta, or m theta, as a function of x. Assume that m and m or m theta act in the positive direction according to the established beam sign convention for positive moment. Do you remember? If I have this beam that upper fibers are in compression, then moment is positive. Or if beam element smiles at you, then bending moment is positive, which means that there is compatibility here between smiling face and the convention for the positive moment. Then, using the same coordinates as before, determine internal moments m caused by real loads. Since positive m and m theta was assumed to act on the conventional positive direction, it is important that positive m acts in this the same direction. Don't use two different coordinate systems. Apply the equation of virtual work to determine the desired displacement. If the algebraic sum of all integrals is positive, then delta or theta is positive, or in the same direction as you want it. Because you asked, what is the displacement in this direction? Okay, you are getting an answer, or positive or negative. If it is negative, that means displacement is in opposite direction, but on the same line. Any questions? Pay attention. I'm not in a hurry. Why? Because I would like you to understand everything. Not almost everything, but really everything. Therefore, in this section, I'm bringing every example. We are considering absolutely every example. Why? Because when you will be reviewing the book, you will know that this we already studied, so that it will be easier for you to comprehend during the study process. Okay, we have a cantilever beam under the distributed load W. I want the tip displacement, B. So here I'm applying this unit load. Okay? Then, so bending moment here when I cut. Okay, that is a cut. That is a real load. Pay attention, here, this value equals, okay, that is x. So the value equals W times x. This load is in the middle. Okay, so displacement between the sum of the forces and this cut equals x over 2. So bending moment equals minus W x squared over 2. That is for real loads. So virtual moment. Okay, here when I cut, that is a cut. Then bending moment equals minus 1 times x. Why? Because upper fibers are in tension. That is how it works. And 1. Oh, that is this bending moment. Virtual moment m. The vertical displacement of point B is obtained by placing a virtual unit load at B. By inspections, there are no discontinuities of loading on the beam for both real and virtual loads. Thus, a single coordinate can be used to determine the virtual strain energy. This coordinate will be selected with the origin of B, so that the reactions of A do not have to be determined in order to find the internal moments. Using a method of sections or method of cuts, the internal moment M is shown here. and that is external moment. Okay, then vertical displacement in point equals integral small m capital M EI dx minus 1x minus wx squared over 2 dx EI. So we get WL in force power 8 EI. Simple as ABC. Any questions? If you have any questions, please do not hesitate even 1 nanosecond. Please send me an email and I will try to explain to you. Okay, determine the slope. Now here that is a slope. At point B, look please, what is the advantage of this method over other methods of integration? Because here, okay, I will write down, maybe I will first solve this and then. We want to find the slope here. So therefore, I'm adding here this virtual moment 1. Okay? So real moment equals, look please, if I cut here, then Vy equals P, and bending moment equals minus Px, P times x. Here, then there is one part and second part. There is discontinuity. Here, naturally, Vy equals 0 and moment equals 0 because there is nothing here. M theta 1 equals 0. Here, if it is on the right-hand side, here, if I do cut here, then Vy is M theta 2 equals 1. And upper fibers are in compression, so therefore this M theta 1 equals positive values. So then we get, look please, 1 times theta B equals M theta M over EI. Okay? In the first part, until L over 2 is 0, because it's M, that is 0. That is minus Px1. Okay, here is minus P, L over 2 plus x2. Okay, here I'm using another coordinate system, okay, x2. Okay. Then this value equals P, L half plus x2. Integral from 0 to L2. Theta B equals minus 3PL squared over 8EI. The negative sign indicates that theta B is opposite to the direction of virtual couple moment. It's against what I anticipated. Any questions? Okay, question. I said 24, it's 25. 25/16. What is the difference between using ordinary differential equations to find displacements and slopes versus virtual force or moment method? So that is a question. You may say, why do I need to know so much? And by the way, I will not tell you, oh, to know too much or very much is good. No, I'm not going to tell you that. Because we are engineers. If I know one method, then maybe I don't need to know another method. Maybe I just stick with one method and that is it. I can always find by my methods, the ones that I prefer, maybe what I want. Okay. In ODE method, you have to solve for entire v of x. And then you will find also what happens in the point that you want. And you will find also displacement in desired point. Here, we directly find what we want. Okay? Any questions? That is not unlike, I will not refrain from giving this example. Imagine you are going to cafeteria and there is this pre-selected meal. Now, if you want to get a steak, then you take the pre-selected meal and then you take from there the steak. So that is this method. Here, that is not a cafeteria, but that is like this method. It's like a regular restaurant. You just say, bring me steak, I don't want anything else there. Don't put greens, don't put potatoes or rice or lentils or anything. Just, I want to get this directly, okay? There in cafeteria, imagine that you are just getting everything in a box. And you get the box, and then from the box you are choosing what you want. Okay? So I will say cafeteria versus restaurant. Actually, we can say gourmet restaurant. Why? Because it's fancy. Suddenly we are imagining the loads or imagining the moment. They are virtual and we are applying. Pay attention. Mr. Bernoulli was before Einstein, but he assumed that imagination was an extremely powerful tool. Any questions? 2516. Now we are coming to the final topic, and I don't know whether I will be able to cover this. If I don't cover this, then next time on Thursday I will give just a very short lecture, which will cover only this material. 2517. Alberto Castigliano was a famous Italian engineer. Now, interestingly, University of Palermo Italy appointed me during my visit there as a Alberto Castigliano, professor. I was extremely happy with that appointment. Alberto Castigliano, professor of University of Palermo in Sicily, Italy. Okay, let us come back to the topic. In 1879, Alberto Castigliano, an Italian railroad engineer, published a book in which he outlined the method for determining the displacement and slope at any point of a body. Okay? This method, which is referred to as Castigliano's second theorem, applies only to the bodies that have constant temperature and material with linear elastic behavior. If the displacement at a point is to be determined, the theorem states that the displacement is equal to the first partial derivative of the strain energy in the body with respect to the force acting at a point and is in direction of displacement. In a similar manner, the slope of the tangent at a point in a body is equal to the first partial derivative of the strain energy in the body with respect to couple moment acting at a point and in direction of the slope angle. Okay, that is a theorem. We are discussing this theorem. To derive Castigliano's second theorem, consider a body of any arbitrary shape which is subjected to a series of forces, small, you see, unfortunately we are using the same notation N as before we had this unit load created distribution of forces in the truss. But that is N is a positive number, P1, P2, Pn. Okay, so that is this P1, P2, P3, and that is P sub N. P sub N. N is a positive integer. Here, okay? According to conservation of energy, the external work done by these forces is equal to the internal strain energy stored in the body. However, the external work is a function of external loads. So that is this U external equals summation integral P dx. So the internal work is also a function of external loads, because they're equal to each other. So U internal equals U external, that is conservation of energy principle. And it's a function of loads, P1, P2, Pn. Now, if any of the external forces, say P sub j, is increased by a differential amount dpj, so that is P sub j. So imagine N equals 100. So there are 100 forces. P sub j is 1 from 100, any. So I imagine j equals 59. That is this 59th force. Then, look please. Now, if one of the external forces, Pj, is increased by a differential amount, dpj, the internal work will also be increased, such that the strain energy will be ui plus dui equals ui plus derivative of ui in pj's direction times dpj. That is differential. Differential, this is very simple. Differential equals derivative times the differential of what is increased. P increased by dpj. Any questions? Now, pay attention. In the test, there will be no Castigliano's theorem related question. Only up to Castigliano's theorem. And I will put this also in Canvas. No Castigliano's theorem, last topic, will not be coming on the test because it would be unfair to give you a material that was not exposed in the lecture, but I would ask you the material. And anyways, I will be finishing this topic during the test that you will be taking. Your test will be administered between 9 to 9:15 to 11:30. I will be lecturing between 9:30 to 11. Okay? This topic will be only coming only if some student does not do the third test well, and we will take a retake. Then naturally, before retake, I will be able to cover this. This will take maybe half an hour or maximum on Thursdays. Then this topic will come in retake also, but not during this test number 3.